Hello students. So continuing the redox reaction, this is going to be our third lecture in redox reaction. In the previous lecture we discussed about the redox types of redox reaction, and then we also balanced the redox reaction. We studied how to balance a redox reaction. So once we are familiar with redox reaction and we are competent with balancing of redox reaction, the next step is stoichiometry of redox reaction. How to correlate the amount of oxidizing agent and reducing agent for further analysis, which is redox titration. So in this lecture we are going to discuss about the stoichiometry of redox reaction. What are the tools we use for solving stoichiometry of redox reaction? Because we all know that solving stoichiometry of redox reaction is really a challenging task. Balancing of redox reaction is not so straightforward, and so the stoichiometry of redox reaction will be definitely a big challenge. So today we are going to discuss the tools which we use for solving the stoichiometry of redox reaction. So first, what do we mean by the term stoichiometry of redox reaction? What do you mean by the term stoichiometry of redox reaction? To understand it, let us start with a very common redox reaction, and then slowly we will develop the concept. So if we have a redox reaction like K2C2O4 plus KMnO4 plus H2SO4 giving K2SO4 plus MnSO4 plus CO2 plus H2O. In stoichiometry of redox reaction, we are going to talk about the relationship between the amounts of oxidizing and reducing agent. So here we have potassium permanganate as oxidizing agent and potassium oxalate as reducing agent. How their amounts are related. One obvious way is to balance this redox reaction. We have discussed in the previous lecture a shortcut method of balancing, and if we apply that shortcut method of balancing, we find that the coefficient here comes out to be 5 and here it is 2. So if we balance this two oxidizing and reducing agent with by shortcut method, we find that they reacts in 5:2 molar ratio. After doing this, it is simple to relate their amounts. So we can say that 5 mole of this will combine with 2 mole of potassium permanganate. But it is not easy to balance a redox reaction all the time for solving stoichiometry of a redox reaction. So there is an alternative for solving this redox reaction, which we call the concepts of equivalence. Using the concepts of equivalence, we can skip the balancing, the tedious balancing of a redox reaction. Without balancing a redox reaction, we can solve the stoichiometry using the concepts of equivalence. So we are going to talk about the concepts of equivalence so far as redox reaction and its stoichiometry is concerned. Concepts of equivalence can be applied in other part of chemistry also. Acid-base titration can also be very easily solved using the concepts of equivalence. But concepts of equivalence works well especially in case of redox reaction. And with the help of concepts of equivalence, a redox reaction can be solved without balancing of a redox reaction. So first thing, if we go to apply the concept of equivalence in redox reaction, is to define equivalent weight of oxidizing and reducing agent, which we denote by E. Capital E is used as a symbol for equivalent mass. We usually call it equivalent weight. Equivalent weight of an oxidizing agent or a reducing agent is defined as equivalent weight is equal to molecular weight divided by change in oxidation number. Change in oxidation number per formula unit of oxidizing agent or reducing agent. So if we divide molecular weight by change in oxidation number for 1 unit of oxidizing agent or reducing agent, it gives a quantity called equivalent weight. Let us apply this formula to some of the oxidizing reducing agent to understand this further better. If we use potassium permanganate in acidic medium as an oxidizing agent, manganese is always converted to Mn+2. So for 1 unit of potassium permanganate, the change in oxidation number is 5. Here we have +7, here we have +2. So equivalent weight of potassium permanganate here is its molecular weight divided by 5. Change in oxidation number for 1 unit of potassium permanganate. Similarly, if we use potassium dichromate K2Cr2O7 in any medium, I am taking acidic but it is same in basic medium also, then potassium dichromate itself is always converted to Cr+3. Here chromium is undergoing change in oxidation number from +6 to +3. But here we have written change in oxidation number per formula unit. And in one formula unit we have 2 chromium. So we'll have to take here 2. So for one formula unit we'll have to take the change in oxidation number for 2 chromium, and for 2 chromium it is 12 2 into plus 6, 2 into plus 3, 6. So difference of 6, oxidation number, difference is 6. So equivalent weight of K2Cr2O7 is molecular weight divided by 6. We must emphasize here in determining this quantity that in the denominator it is the change in oxidation number per formula unit. If we take one more example of K2Cr04 potassium chromate giving Cr plus 3 in a redox reaction. Now again chromium is undergoing change from chromium plus 6 to plus 3, but now change in oxidation number is 3 only. It is because in one potassium chromate we have one potassium. In one potassium chromate we have one chromium. So now we need to take a difference for one chromium only, and that will be 6. So here also plus 6 to plus 3, but in one formula unit we have 2 chromium, so we'll have to take difference for the 2 chromium. Here 1 chromium in one formula unit, so difference for 1 chromium will have to be taken only. And therefore for potassium chromate its equivalent weight will be molecular weight divided by 3 only. So we have defined a quantity called equivalent weight, which is molecular weight divided by change in oxidation number per formula unit. This change in oxidation number per formula unit has also been given a name in redox reaction, and it is usually called N factor. So with this we can say that equivalent weight is molecular weight divided by N factor, and N factor is change in oxidation number for one formula unit of oxidizing agent or reducing agent. So we have just derived a formula for determining equivalent weight of an oxidizing reducing agent. So we can say that N factor is the ratio of molecular weight divided by equivalent weight. So here we have derived a quantity now, N factor, which is related to molecular weight and equivalent weight. Then comes the second quantity in this series, that is number of gram equivalent. Number of gram equivalent. Number of gram equivalent is related to equivalent weight. Number of gram equivalent is related to equivalent weight, as number of mole is related to molecular weight or molar mass. Number of gram equivalent. Number of gram equivalent, which is denoted by EQ. Number of gram equivalent in a given mass of oxidizing or reducing agent is determined as mass divided by equivalent mass. So number of gram equivalent is related to equivalent mass in the same manner as number of moles is related to molecular mass. Molar mass, as we all know, number of moles N is equal to mass upon molar mass. So if we want to relate this to, we can write a relation as number of equivalent divided by number of mole will be equal to, if we divide this to, molecular weight will come in numerator, so molar mass divided by equivalent mass. And molar mass divided by equivalent mass is nothing but n factor. So this is important relation we have derived here. If we know number of moles multiplied with n factor to determine the number of gram equivalent, or if we know the number of gram equivalent, divide it by n factor to obtain the number of moles. So number of equivalent, number of moles, they are related. If one is known, other can be known using n factor. Let us apply this to one or two case. Suppose if we have, say, in a chemical reaction, in a redox reaction, in which KMnO4 in acidic medium is getting converted into Mn2+. Suppose we have its 4 mole. We want to convert it into equivalent. It would be equal to, see, number of moles multiplied by n factor, and n factor here is 7 minus 2, 5. So 0.4 into 5 to equivalent. And suppose if we have one equivalent and we want to convert it into mole, then number of equivalent divided by n factor gives number of mole. So 1 divided by 5, that is 0.2 mole. So mole can be converted into equivalent, equivalent can be converted into mole as and when required. Now, once we know how to determine the number of gram equivalent, let us know about the law of chemical equivalence, which will be used in this chapter for solving stoichiometry of a redox reaction. Law of chemical equivalence. Law of chemical equivalence states that in a chemical reaction, same number of gram equivalents of all the reactants combined. So law of chemical equivalence this is going to be the principal law for solving stoichiometry of a redox reaction. According to this law, in a chemical reaction, same number of gram equivalent of reactants combines. same number of gram equivalent of reactants combines to give the equal number of gram equivalents of products. So in simple word we can say that in a chemical reaction, number of gram equivalents of reactant combining are same, and the number of gram equivalents of products formed are also same, and that is also equal to the number of gram equivalent of reactant reacted. Better we apply this once in a redox reaction, and then we will try to understand what it is saying. So if we take a redox reaction like K2Cr2O7 plus say iodine in acidic medium, say gives KiO3 plus Cr2SO4 whole 3 plus K2SO4 plus H2O. Then according to this law of chemical equivalence, equal number of gram equivalent, one equivalent of this will react with one equivalent of this. Now let us verify it. If we balance this redox reaction, we find that for one dichromate the change in oxidation number is 6. For one I2 the change in oxidation number is 10. Here iodine is in plus 5. So for I2 we'll have to put here 2 and then plus 5 into 2, 10. We have a common factor here, 3 and 5. So when we balance, we find 5 here and 3 here. This is the stoichiometric coefficients of oxidizing and reducing agent in the balanced redox reaction. Also, N factor of dichromate is 6. N factor of dichromate is 6 and that of iodine is 10. I2 giving 2 KiO3, so total change of oxidation number is of 10 unit. So if we convert the number of equivalents into mole, we find number of moles 1 by 6, 1 by 10 mole, number of equivalent divided by N factor. If we rationalize it, we have a LCM of 30. So if we multiply this 2 by 30, we obtain here 5, here 3. So one equivalent if we take, then their molar ratio will be 5:3, and we have already seen that they react in 5:3 ratio. So for relating their moles 5:3, we will have to balance them. But for applying concepts of equivalence, we don't require to balance the redox reaction. We just say that same number of gram equivalent will combine. Not only that, If the reactants are not in a stoichiometric amount, then we can say that the one having less number of gram equivalent will act as a limiting reactant, and the other in excess will be left some unreacted at the end of reaction. So finding limiting reactant is also very simple using the concepts of equivalence. So with the help of concepts of equivalence, the stoichiometry of redox reaction can be solved very easily. Next, there are some common oxidizing agent and some common reducing agent whose reactions are fixed in most of the redox reaction, and therefore their N factors are also fixed. And for those reactions, informations are not usually given in the question. We have to derive on our own that for these oxidizing agents these products are formed, and this is the N factor for this reaction. So let us make a table of common oxidizing agent, common reducing agent, and their corresponding half reaction, N factor and all, so that we can use them for solving a stoichiometry of redox reaction. So next we are going to see some common oxidizing agent and some common reducing agent, so that their N factor can be used for applying the concepts of equivalence. So we are going to make a list of common oxidizing agent and common reducing agent. So let us make a list of common oxidizing, common reducing agent. First, let us take common oxidizing agent. Medium play an important role in a redox reaction. The same reagent reacts differently in different medium. So medium must be specified. Half reaction, and N factor. The first and the most common oxidizing agent is potassium permanganate. If potassium permanganate is used in acidic medium, the corresponding half reaction would always be permanganate ion giving Mn2+. And so in acidic medium, N factor of potassium permanganate is always 5:7:2. So always 5. But if the same potassium permanganate is used in dilute alkaline medium or even neutral medium, permanganate is converted to MnO2, and in that case the change in oxidation number will be 7 to 4, so 3. Manganese dioxide also acts as an oxidizing agent in so many redox reaction, and it acts as an oxidizing agent in acidic medium only, and MnO2 is converted into Mn2 plus, so N factor will be 2, 4 to 2, manganese from +4 to +2. So they are the common oxidizing agent derived from manganese. Then potassium dichromate is another very common oxidizing agent. It acts as an oxidizing agent in any medium, acidic or basic, and dichromate always converted into Cr+3, so N factor will be 6 for 2 chromium, change will be of 6 unit in oxidation number. But we have just seen if we use K2CrO4 potassium chromate, then the change in oxidation number will be of 3 unit only. There is 1 chromium only. Then comes XO3 minus, that is also a very common oxidizing agent, where X could be chlorine, bromine, iodine, and if medium is acidic, then it is converted to X2 and change will be for 5 unit. Change will be of 5 unit. X2 also act as an oxidizing agent in acidic medium, and it gives X minus, change will be of 2 unit. Here X is again chlorine, bromine, iodine. H2O2 is also used as an oxidizing agent in any medium. H2O2, if act as an oxidizing agent, it gets reduced to H2O, so change will be 2 minus 2 minus 4. For 2 oxygen will have to balance minus 4. So these are some of the common oxidizing agent which we need to remember or learn, because if these reagents comes, then information will not be given that what are the products, what is the N factor for the reactions. Then let us move to some common reducing agent. Some common reducing agent, and like oxidizing agent, if those reducing agents are used, then the information will not be given that what are produced in the redox reaction for this reducing agent. So now common reducing agent, we would write common reducing agent here. The rest of the things are same. The most common reducing agent is iodide, which could be given in the form of Ki, NaI, etc. They act as a reducing agent in all medium, but preferably acidic medium is used. Then only we can say with guarantee that iodine is going to be formed. So in acidic medium, iodide is converted to iodine. N factor here is 1. The reason being, for one iodide we have to find out the change in oxidation number. For one iodide, minus 1 to 0. So N factor is 1. Another common reducing agent is oxalate. It could be given in the form of oxalic acid or salt K2C2O4 or even KHC2O4. In any medium, they act, all of them act as a good reducing agent, and the reducing species is oxalate in all cases where it is converted to CO2. If we find the N factor here, it is 2. Carbon on left has +3 oxidation state, on right it has +4. So change of 1 for one carbon, but in one oxalate there are 2 carbon. So per formula unit we'll have to see change for 2 carbon. So N factor of oxalate is 2. Then ferrous iron is another common reducing agent. It acts as a reducing agent usually in acidic medium, and ferrous iron is oxidized to ferric iron. So N factor 1. Sulfide ion also acts as a reducing agent, and in acidic medium, sulfide ion is oxidized to SO2. So -2 to +4, 6. S2O3 2-, thiosulfate. Now in general, it is converted into S4O6 2- when treated with iodine. This is very specific. In other cases it reacts differently, but if reacted with iodine, it is oxidized to S4O6 2-, and in that case N factor can be determined. It comes out to be 1. This is a very important reaction, that's why I have written here, but it must be mentioned that it is only with iodine. H2O2 also acts as an oxidizing agent. If used as an oxidizing agent in any medium, it is oxidized to, it is used as a reducing agent, it is oxidized to O2, so -2 to 0, and factor 2. We can see H2O2 is there in oxidizing agent list as well as in reducing agent list. So it is a mild oxidizing as well as mild reducing agent, and therefore the behavior of H2O2 depends on other reagent. If H2O2 is used with oxalate with iodide, it will act as an oxidizing agent because these are the strong reducing agent. But if H2O2 is used with potassium permanganate, it will act as a reducing agent because potassium permanganate is a strong oxidizing agent. So these are the some common oxidizing reducing agent and their corresponding N factors. If these reactions are used, we must know their half reactions and N factor, because these half reactions and factors are not usually given in the question. So now we are familiar with common oxidizing, common reducing agent and their N factors. The next step is to define a new concentration unit, normal T. In mole concept, we have learned different type of concentration units, molarity, molality, and mole fraction, several this type of concentration units. Today we are going to define a new concentration units which is mainly used in redox reaction, that can also be used in neutralization titration, but redox reaction uses this concentration unit normality the most in order to make the calculation simple. So next step towards stoichiometry of redox reaction we are going to talk about is normal T. Normal T, how normal T is defined, let us see and analyze it. Normal T usually denoted by capital N. Normal T is the number of gram equivalent. Normal T is the number of gram equivalent of a solute present in 1 liter of solution. So it is the number of gram equivalent of solute present in 1 liter of solution. So if V liter of solution contain EQ number of gram equivalents of solutes, then we can say that normal T will be number of gram equivalent per liter of solution. It must be mentioned that the volume here is in liter and the numerator is number of gram equivalent. So normal T is the number of gram equivalent of solute present in V liter of solution, present in 1 liter of solution. This normal T is parallel to molarity. So it must be related to molarity. Molarity is simple in expression. First we form a solution in terms of molarity concentration, but normal T is easier in calculation, so we convert molarity into normal T. So if we recall, molarity, it was number of moles upon volume in liter. And if we want to relate this to normality divided by molarity will be equal to, volume will cancel off, number of gram equivalent divided by number of mole, and it is nothing but n factor we have just defined, which is also molecular weight upon equivalent weight. So knowing this relation, a lot can be done in redox reaction. If molarity is known, normality can be known. If normality is known, molarity can be known. Similarly, number of mole, number of equivalent can be related. So let us apply this to see in some of the example that how they works, how they are used. Suppose if we have in any redox reaction potassium permanganate as an oxidizing agent in acidic medium. In question it is given that the molarity of potassium permanganate is say 0.06. But we want to know normality. Just now we will see why we want normality. But suppose if we want to know the normality of this solution, so normality is molarity multiplied by n factor, and for potassium permanganate we have just tabulated and have seen so many times that n factor of potassium permanganate is 5. So it will be 0.06 into 5, 0.3 normal, usually written as 0.3 n. So 0.06 molar solution of potassium permanganate is also 0.3 normal. If we have potassium dichromate solution, and if its molarity is given 0.04 molar, its normality will be 0.04 into 6, n factor is 6. So 0.04 into 6.24 normal. So if molarity is known, normality can be known. Why we are converting this molarity into normality? That is very straight to understand why we are converting this molarity into normality. We have just defined normality as the number of gram equivalent of solute present in 1 liter of solution. Number of gram equivalent of solute present in 1 liter of solution. So if we multiply normality by the volume of solution, we directly obtain the number of gram equivalent. We obtain the number of gram equivalent. So number of gram equivalent is normality into volume. But be very careful when using this relation. Here the volume is in liter. Let us take an example. Suppose we have 50 ml 0.02 molar KMnO4 solution in acidic medium. Now we want to know the number of gram equivalent of potassium permanganate in that solution. So first we convert molarity into normality. Molarity multiplied by n factor is normality. So 0.02 into 5, it is 0.1 normal. And normality multiplied by volume gives the number of equivalent. So it would be equal to normality 0.1 multiplied by volume, which is 20 upon 1000 liter. It is milliliter. So it will be 5 into 10 raised to the power minus 3 equivalent. Volumes are usually given in milliliters, so we always obtain this factor of 10 ka power minus 3, which is called milli, factor of milli. So it can be written as 5 milli equivalent. 5 milli equivalent. So if we multiply normality directly by volume in milliliter, we will obtain milli equivalent rather equivalent. So we can redefine as volume in milliliter multiplied by normality gives milli equivalent. So if we divide milli equivalent by normality, we obtain volume. So these three can be related: milli equivalent, volume, and normality. Here volume is in milliliter. It is convenient to adopt this milli equivalent form because we always get volume in milliliter. Small volume is used. So normality is used to determine the number of gram equivalent. And once we know the number of gram equivalent of oxidizing agent, we can say that same number of gram equivalent of reducing agent will be required to react with this oxidizing agent. So for solving stoichiometry using the concepts of equivalence, we can determine the number of gram equivalent of one and then we say that same number of gram equivalent of others would be required. And for that purpose, balancing of a redox reaction will not be required. So with the knowledge of concepts of equivalence, we can skip the balancing of a redox reaction. So let us apply these fundamentals for some correlation so that we can further understand the concepts of equivalence, which we will be using in the redox titration, our next topic. So suppose we have been given a situation that 20 ml potassium permanganate solution is required for oxidation of 30 ml 0.075 molar ferrous sulfate solution in acidic medium. What is normality and molarity of KMnO4 solution? It's a very simple situation. So 20 ml KMnO4 reacting with 30 ml 0.075 molar ferrous ion. Ferrous ion will be oxidized to ferric ion. So N factor of ferrous ion is 1. So it is 0.075 normal also. If we multiply these two, that gives the milli equivalent of ferrous ion, and that will be same as the milli equivalent of potassium permanganate, because same number of gram equivalent of ferrous sulfate and potassium permanganate will react. So if N is normality of this KMnO4, volume multiplied by normality on this side will be equal to volume multiplied by normality on the other side. So if we solve for normality, 1, 0 will cancel off. So normality is 3 by 2 times 0.075. If we simplify it, it is for KMnO4. So 3 5 ja 0.2. So it would be somewhere around 0.1125 normal. That is the normality of original potassium permanganate solution. And in acidic medium, N factor for potassium permanganate is 5. So molarity will be normality divided by 5, and it would be 0.1125 divided by 5. So 0.02 5 molar. So this way we determine normality, molarity and correlate them. Let us take one or two more example. Suppose if we have another similar situation, it is asked that how many milliliter of 0.015 molar K2Cr2O7 solution would be required to oxidize 25 ml 0.03 molar K2C2O4 solution. How many milliliter? So now we can say that once again the total gram equivalent of potassium dichromate required will be equal to gram equivalent of potassium oxalate, and for that we'll have to convert both molarity into normality. So 0.015 into 6 normal K2Cr2O7. On the other side, N factor of dichromate is 6. On the other side, 0.03 into 2 normal of oxalate. So it is 0.06 normal. On this side 15 6 are 90, so 0.09 normal. Volume of oxalate given is 25 ml. Volume of dichromate is asked. So normality multiplied by volume will give milliequivalent of potassium dichromate. Normality multiplied by volume will give milliequivalent of oxalate, and they must be equal in order to complete the redox reaction. So 0.09 into V will be equal to 0.06 into 25. If we solve for V, this V will be equal to 6 into 25 divided by 9. So 3233, 25 into 250 upon 3. So it would be somewhere around 16.67 milliliters. So this much volume of potassium dichromate would be required for oxidation of 25 ml 0.03 molar potassium oxalate solution. Let us take one more example for practicing purpose so that we become confident in this type of things. So let us take one more example. What volume of 0.05 molar acidic KMnO4 required for oxidation of 30 ml 0.025 molar FeC2O4 solution. Now the situation is a bit tricky. Now we have taken ferrous oxalate, which when react with potassium permanganate, both ferrous ion and oxalate ion are oxidized. So in ferrous oxalate, for one formula unit we have one ferrous and one oxalate. Ferrous is oxidized to ferric, so for one ferrous changes of 1, it is oxidized to CO2, so for one oxalate changes of 2. So for one molecule of ferrous oxalate there is total change of 3 unit in oxidation number, so its n factor is also 3. So once again, milliequivalent of ferrous oxalate will be equal to milliequivalent of potassium permanganate. Milliequivalent of KMnO4 is equal to milliequivalent of FeC2O4. Milliequivalent of potassium permanganate will be equal to normality 0.05 into 5 into volume is equal to milliequivalent of ferrous oxalate normality 0.025 into 3, 0.025 into 3 into volume 30. So V is equal to 0.025 into 90, 30 into 390 divided by 0.05 upon 5. So it is 2552, 518. Oh, only 9 ml. So 9 ml of potassium permanganate would be required to oxidize 30 ml of 0.025 molar ferrous oxalate solution. Let us take one more situation. To understand further this concept, a situation is given in which 20 ml acidic KMnO4 solution is required for oxidation of 25 ml of a Ki solution. Oxidation of 25 ml of a 0.1 molar Ki solution. What volume of same KMnO4 solution would be required for oxidizing 30 ml of a 0.1 molar Na2S solution. From the first information, we can determine normality of potassium permanganate. So, milliequivalent in case 1, milliequivalent of KMnO4 is equal to milliequivalent of Ki. For Ki, n factor is 1, so its molarity is also normality. So 20 volume into normality of potassium permanganate will be equal to normality into volume 25 into 0.1. So normality of KMnO4 solution is 25 upon 20 into 0.1. 5 4 ja 5 5 ja. So it is 0.125 normal. In the next case, KMnO4 is reacting with sodium sulfide, where sulfide will be oxidized to SO2. So, in case 2, milliequivalent of KMnO4 required is equal to milli equivalent of Na2S. Normality of permanganate is now known. So let volume is V, potassium permanganate volume is V multiplied by normality 0.125. So volume of permanganate into normality will give milliequivalent of potassium permanganate, and that will be equal to milliequivalent of sodium sulfide. And sodium sulfide milliequivalent will be volume multiplied by normality 0.1 into 6. Here S2 minus will be converted to SO2, so n factor 6. So the required volume will be 30 into 6 into 0.1 divided by 0.125. If we solve it, let us put 20 here, so decimal will cancel off. So 25 4 ja 25 5 ja 5 6 30. So it is 6 into 6 36 into 4 144 milliliter. 144 milliliter. So with this fundamentals and exhaustive demonstration of the concepts of equivalence, we have developed a very strong and sound concept of concepts of equivalence. We can convert any quantity related to redox reaction into other desired quantity, say molarity to normality, normality to molarity, number of gram equivalent to number of mole, vice versa, and that would be of very great help when we will start solving the problems of redox titration in the next lecture.